Welcome to our next talk by Vlad Khononov and Sonya Natanzon, Pragmatic Approach to Architecture Metrics. Please welcome the speakers.
Good morning, everybody. I love the mid-morning session. I so rarely get that when everybody's already awake but not too hungry yet. So, as is proper for any software conference, we'll do some famous quotes today, and we'll start with this one by author and management consultant Peter Drucker. What gets measured gets managed. I hear this quote a lot at my work, and usually it comes with a request for metrics. Well, it turns out that Drucker never actually said that, according to the Drucker Institute. And a little bit of digging reveals an origin for this quote. It was actually said by a guy named Simon Calkin, who was reviewing a paper titled Dysfunctional Consequences of Performance Measurements. And the quote that you see is the summary of the paper. Starts out the same, but takes a real left turn after that. What gets measured gets managed, even when it's pointless to measure and manage it, and even if it harms the purpose of organization to do so. Lots of skepticism about this metric-obsessed culture. So what does that mean? Not everything that matters can be measured, and not everything that can be measured matters. We've seen plenty of bad metrics out there. Just think of number of lines of code as a metric of engineering productivity or architectural complexity. Easy to take that one out of context, misinterpret it, very easy to game it. So today we're going to talk about what it means to measure your architecture, what matters and what doesn't, and how to stay pragmatic in your approaches. Quick word about us. We're both somewhat of a metric skeptics when it comes to software architecture. So it made it for a fun challenge to put our lived experiences into a structured approach. We both have seen metrics lead to suboptimal outcomes, unintended consequences, so we wanted to identify what matters, how to measure it. That's assuming if it can be measured at all. My name is Sonya Natanzon. I'm a software architect. I lead engineering teams, and today I'm going to present strategic business-focused architecture metrics.
Hey, good morning, everybody. My name is Vlad Khononov. You probably know me by the Monkey Book, Learning Domain-Driven Design. Today, I don't want to talk about domain-driven design, but about my love-hate relationship with software metrics. And I will try to explain why it's way more towards the hate side than the love side.
All right. So let's start with some assumptions. Everybody wants to know if they're successful. Even software architects, maybe especially software architects. They want to know if the architecture is built as working, and the business that probably paid a good money for that architecture wants to know if that architecture is working for the business. And everyone wants to have quantitative metrics to prove success. Nobody likes to go on qualitative or feelings. I feel this architecture is working pretty well for me. Certainly much harder to argue that against thanks to our new architecture, our web pages are loading in half a second or less. Lastly, software architecture is difficult to measure. Why is that? Well, it's hard to define what software architecture is in the first place. And success of software architecture really lies in its long-term goals, so it gets difficult to find short-term or immediate metrics that will identify success. If the web pages are loading in half a second or less now, will they still do that in 2 years? Is it even going to matter in 2 years? So I just said that software architecture is difficult to define, but there is a widely used definition out there, which brings us to the second famous quote of the day. Architecture is about important stuff, whatever that is. As definitions go, it's still pretty nebulous. What exactly is important to software architecture? We're going to want to know what that is, and we're going to try and measure it. The second thing that we know is the purpose of software architecture is to solve a business problem, support business objectives. Without solving a business problem, software architecture becomes a bit of an academic thought exercise. All of your architectural decisions have an objective, and that objective is given to you by the business, the problem that you're solving for the business. So if the architecture is about important stuff, and architecture's purpose is to support business goals, we can derive that what's important to the architecture is whatever's supporting those business goals. Okay, so now we're starting to get somewhere. To know what to measure, let's identify the qualities of software architecture that are important for solving those business problems, supporting business goals, and let's see if we can measure them. But can we really do that? Can we identify common traits of a software architecture that are important to all businesses? Businesses are different. Some are really different from one another. Are there such qualities that we will want to measure? Well, it turns out that there are, and I can describe them in 2 words: evolution and scale. Regardless of what the business is, its capacity to evolve and change, and its capacity to scale out is critical to its survival, and therefore needs to be supported by the software architecture. I can show this by looking at a typical product life cycle. So this is a path of a typical successful product evolution. I say successful because if the product is not successful, if it can't find its market niche, it's going to die. And if the company can't pivot, can't change, it's going to die right along with it. At the early stages of inception, refinement, evolution, there are rapid changes taking place to shape the product and to find that market fit. It looks really nice and linear on the slide, but really, the original idea can go through some pretty dramatic pivots and transformations before it reaches the market. And Vlad, in fact, you have a really good example of an early stage startup that went through those transformations.
Yeah. In fact, I was working for a startup company a few years ago that started in the online marketing field. Then a year later, we switched to gaming, but eventually found the success in fintech. So yeah, during the first 2 or 3 years, we used the same solution, but tried to address different problems in different business domains.
Wow, a whole different verticals even.
Yeah.
So in the later stages, when the product is adopted by the market, hopefully has some loyal customers, business will want to scale out to fulfill the unmet need. And this could mean a number of different things. This is larger quantity, lower costs, fewer defects, faster production, any combination of those things. If we look closely, both evolution and scale are different aspects of business's ability to change. And again, since what's important to the software architecture is to support the business goals, we want to make sure that our software architecture can change according to the business needs. It is that ability to change that we will want to measure, and it is that common thread that's going to be important in software architecture for all of the businesses out there. When we combine a product life cycle with vectors of change, of evolution and scale, we get this product maturity curve. Its axes are change frequency and change effectiveness, and they start to differentiate what's important to a product life cycle at different stages. At the idea, inception, evolution, we want to have many fast changes, hopefully that take a little bit of effort, not a lot of effort, that are low friction, but maybe they don't always hit the mark. And at that stage, that's okay. The product is still taking shape, it's young, customers are few, if any, and what's the worst that can happen? We'll just make more changes to find that market fit. At later stages, when you do have customers with expectations of stability, with expectations of quality, changes become less frequent, but they become more targeted and more effective, with a lot more focus on value being added and making sure that the disruption to existing customers is low. I happen to work at a company that's going through a transformation like that, and what I measured as success a couple of years ago, which was our ability to launch products really fast, is no longer that important. It gave way to operational excellence and rapid scale. As your business evolves and changes, so does your architecture, and so does the focus of its metrics. What we're measuring overall is still the same. It is change frequency and change effectiveness, but we no longer focus on frequency. The focus completely shifted onto effectiveness, which is value to the customers, and quality. So now I'd like to introduce these 4 metrics to you. Change lead time or cycle time, deployment frequency, hopefully entirely self-explanatory, change failure rate, and mean time to restore. If these metrics look familiar to you, it's probably because you've read Accelerate book or are familiar with DORA, the DevOps Research and Assessment Team. Even though these metrics come to us from the world of DevOps, we can easily adapt them for measuring the success of our software architecture. If we think of these as architectural qualities that support our vectors of change, we can see them as now individual measurements in these broader categories. Change frequency is going to encompass cycle time and deployment time. How long does it take to build a change? How long does it take to deploy it? Does it have to sit on the shelf while you put a bunch of changes together and wrangle a complex deployment? Under change effectiveness, you have your change failure rate and mean time to restore. And that one is interesting because what does change failure look like? Is it just a basic system outage? Is it a failure of a change to bring value to your users? And how long does it take to recover from either that basic outage or maybe from customers that went over to your competitors instead? There is a lot of nuance that you have to go through as you're defining these metrics and creating these metrics for your software architecture. Let's talk about how we can measure these pragmatically. And what I focus on is data collection and analysis rather than tooling and automation. But most importantly, what I focus on is making sure that we don't take away from the primary objective, which is continuing to support business goals. Your first responsibility as an architect is to define your measurements. How do you define your cycle time in order to measure your change frequency? Where does it start? Does it start when a product manager dreams up a feature? When it gets approved to go forward? With a user story? With an engineer starting to code it? Where does it end? Does it end with deployment? Feature flag being turned on? Let's see. First user starting to use it? Maybe beta user, or maybe feature going to general availability. How do you define change failure if you're measuring your effectiveness? Is it basic downtime? Is it multiple support tickets that are coming in after your product went live? Is it customers going to competitors and you losing revenue? Make sure you create these definitions, circulate them with your stakeholders, write them down and have them as your KPIs, your OKRs. If you don't do this, somebody else will do it for you. And you probably won't agree with those definitions, so get ahead of that. Log multiple data points. You don't always know what's useful in the beginning. And if you can leverage your existing systems rather than creating new ones, so this will be your ticketing system for either implementation or support, your log aggregation system, your observability tools, or maybe metrics that already exist, like your daily active users, use that. You're going to go through rounds of iterations and refinement to understand what's useful and meaningful. Architecture metrics are difficult because of their very definitions. Don't invest too early. Early investment into metric automation. Don't invest too early in automating them. Metric automation leads you to the sunk cost fallacy. I've automated this, I created some tooling, I am going to keep measuring this, even though it may not really be meaningful or relevant anymore. Now, if you already have systems that are automated, that are source of your metrics, like let's say your CI/CD pipeline for deployment frequency, the next point is going to be super important. Don't ever show the output without giving context. I learned a long time ago that numbers pretty much never speak for themselves. They can be interpreted in many different ways. Recent example, recent history, feature, important feature went live, immediately metrics were pulled, and they looked bad. They looked really bad until we said, wait a minute, this is still beta, and there's like a total of 3 users, so this is statistically irrelevant. Can we wait until we get to general availability and we've refined it before we actually look at it? Anything like an employee satisfaction survey. Have you ever read those? We do those twice a year. First time looks like everything is great, everybody's happy. Second time it looks like everybody's ready to quit. What happened? Well, first time was January, and everybody just came back from holidays and happy and ready to work. And second time was in July after a product death march when everybody's ready for a vacation. So context is going to be really, really important. So if you're showing outputs, make sure you have those defined metrics. Make sure you have your data collection methods and any kind of trade-offs, context, and other important information in the same place. Your deployment frequency metric might mean that you're doing an amazing job getting value to customers. Might also mean that every single one of your deployments requires multiple patches and fixes going out. So these were some really simple ways of measuring your architecture, specifically its ability to change on the 2 vectors of frequency and effectiveness. Nothing's ever so simple, so there is a word of caution that I want to give you, and that caution goes by Goodhart's law. Goodhart was a British economist who said that any observed statistical regularity will tend to collapse when pressure is put on it for control purposes. That's a really fancy way of saying that when measure becomes a target, it ceases to be a good measure. That's a way of saying that once you start targeting specific metrics, you get unintended consequences. Your incentive becomes completely perverted. The original intent is to really understand how your architecture flexes. And the story of Cobra effect is a very old and very good illustration of those unintended consequences. When back in the day, when British government was really concerned with a bunch of cobras in the city of Delhi, so they put up a reward for bringing in cobras to reduce those numbers. What happened? Well, citizens of Delhi started breeding cobras and bringing them in for a reward. Of course, nothing lasts forever. Government found out, reward went away. So what happened then? All those cobra breeders no longer needed the cobras, so they just let them back out in the wild. And Delhi arguably ended up with more cobras than it started with. What targeted metrics have I seen that lead to those unintended consequences? Code coverage is a fun one. We always have that, what do you need to pass, 60, 70, 80%? So to get to that, we automate our tests for something simple, maybe getters, setters, CRUD operations. And then there's that 30% of really gnarly business logic or integration code that nobody wants to touch. So do we achieve the goal of having well-tested code? Probably not. Pre-production bugs. Whenever we incentivize finding those, the test team starts logging everything, including tiniest little things that could just be resolved with a quick conversation. Completely disincentivizes collaboration between dev and test. Unintended consequences. Production defects. Those are the bugs that actually escape to production. If we target those, hopefully low, what ends up happening is we expend a lot of energy on discussing, was this a production defect? No, I think this was a missed requirement, maybe an enhancement request. No, that was actually bad data that we're dealing with. That energy is so much better spent on fixing things. Deployment frequency, once again, if you target that, you get a lot of engineers doing little deployments, which probably do not bring a lot of value to customers. That is the arbiter of value, and we just do this for, let's hit the target of frequent deployments, but the value is really questionable. Crash rate, another one that makes it really easy to focus on an easy problem rather than an important one. So in summary, just really exercise caution if you or somebody else puts targets on your metrics, and do look out for unintended consequences. There's one more metric that underlies both change frequency and change effectiveness, and that is change cost. What is the total cost of change? In opportunity, in time, in money, in engineering hours, in inability to solve a more important, more impactful problem. If we were to put change cost on the graph, we can express it as a vector that is proportional to our change frequency and change effectiveness. In order to make more frequent changes, you need to invest. Bring in more engineers, get better tooling, better automation. In order to make more effective changes, you also need to invest, but probably differently. Better UX, better regression suite coverage, still an investment. So making more frequent changes costs more, making more effective changes cost more. Change cost is not a standalone metric. It's a sum total of all of our change metrics. And as architects, we're often asked about change cost. Actually, what we're asked for is how do we keep that cost down? And how we do that is with trade-offs. We identify what's more important and focus on enhancing it while taking away from something else. If you think about the product lifecycle, it's all about trade-offs. Early part of the lifecycle, it's all about change frequency at the cost of effectiveness. In the later one, it's all about effectiveness at the cost of frequency. And by doing that trade-off, we continue to keep that cost linear and proportional to the more important metric. Of course, sometimes business wants to do both. And for both, we incur a cost of changeability, and that now becomes super linear to change frequency and effectiveness. That cost can be prohibitive, and it can be unnecessary, too. There is no return on investment for making frequent changes to a product that's stable, or, for example, a product that's highly regulated and can't really change all that often. And last but not least, these changes have an important common factor that directly affects change cost, and that is change complexity. Complexity is the keystone. It's the predictor of how all your change metrics will perform. It resists everything. It's going to make your lead time longer. It's going to make your deployments less frequent, failures more frequent, and recovery time longer. Complexity also tends to be very contextual and multi-layered. It's essential versus accidental, it's business versus technical, internal versus external, complexity of software itself versus complexity of using the software. Since complexity resists our four metrics, and all four metrics factor into our cost of change, our cost of change becomes proportional to the complexity of change. We kind of know this already. When something is complex, it's that much more difficult to change. It's going to break more often. It's going to be that much harder to fix. You can get a good idea of how your metrics will perform if you understand the complexity behind that change. A lot has been said about complexity, evaluating and measuring it. Probably none better than by my co-presenter, who literally wrote a book that addresses just that subject. How do you pragmatically measure complexity? We kind of know what it is. It's the software that doesn't fit in our heads, but nobody wants to go on qualitative metrics. So Vlad will take us through the pragmatic approaches for measuring complexity.
Thank you, Sonia. And you know what? I want to follow your example and start with a definition. So what is complexity? A rather cute definition of complexity comes from one of my heroes, physicist Geoffrey West, and he says complexity is something that you know it when you see it. Like when you're looking at a big ball of mud, you don't need a metric to tell you that, right? You just know it, that that's a mess. Now, yeah, this definition is cute, is intuitive, true, but we need something more elaborate in order to manage the complexity. So let's take one from the KanDDDinsky framework. Dave Snowden, the author of the framework, he says that complexity is all about the relationship between an action and its outcome. Let's say you're working on a system, you're doing something, changing something, and you know exactly what's going to happen as a result of the change. Well, you're lucky. That's not complexity. That's a simple system. If, however, let's say you're not sure what's going to happen, but you can ask somebody, you can consult some expert, and that expert will tell you what's going to happen. That's not complexity as well. That system is complicated. However, if the only way to find out the outcome of an action is to conduct a safe experiment, or in other words, you won't know what the outcome is going to be unless you make the change and observe the outcome, then you're dealing with complexity. And of course, in our software engineering domain, we have plenty of examples of complexity. First, let's say you have to implement a new business requirement or change some existing functionality. You're looking at the code base and you have no idea what modules need to be changed. That's complexity. Or let's say you do know what you need to change. You make a change, but you have no idea what's going to break as a result of that change. Complexity as well. Now, what causes that complexity in code bases? Because, when we are writing business logic, it's sort of deterministic. Even if it's asynchronous, the business logic is still somewhat deterministic. There are some quantum fluctuations, but trust me, they're not going to affect your if statement. It's going to be deterministic. But still, we end up with complex systems. What causes that? Well, it turns out complexity is not only about the system itself, but it's also about us. And in the 50s, they did an experiment that concluded that we can hold in our heads 7 ± 2 units of data. And then 50 years later, they repeated the experiment, and now it's 4 ± 2. Let's wait for the results in 30 years from now. It's going to be interesting. But anyway, we have our cognitive limits. And to manage the complexity, we have different tools like frameworks, libraries, design patterns, architectural styles. All of them promise us to make things simple. And of course, since the topic of our talk is metrics, let's talk about that thing in the middle, metrics. And as I said in the introduction, my relationship with software metrics is love-hate, much more towards hate than love. And yeah, there was a time when I was trying to be a metrics cop, like I configured this CI pipeline that executes static code analysis and it observed if some metric goes beyond the threshold, alerts would fire up and, we would have to fix the code. We hope that if we keep those thresholds, those targets aligned, the code will be manageable and easy to evolve. Not even close. Let me show you why. Let's say we have this abstractness metric. And this one is about abstract types in a module versus other types. You simply take the number of abstract types divided by concrete types, and you get the abstractness metric. Now, what happens if this metric becomes a target? How hard it is to add abstractions? It's very easy, right? It's like in Sonya's example of Goodhart's law. You're breeding cobras in your code base. You're just adding abstractions that nobody needs, and they're probably going to be ineffective and useless. A closely related metric is instability. This one is about coupling. So here you take the number of types that you depend on divided by the number of overall connections going in both directions, and you get that instability metric. The idea here is that the more types you depend on, the less stable your module is. Because, well, if you depend on, let's say, on 100 other modules, if one of them chances are that you will have to change your module as well. Sounds good in theory, but let's see how it works in practice. So let's say I build this beautiful system. It consists of only one component, and as you can see, there are quite a few other components that depend on my module. And my module have only one outgoing dependency. That's it. If we run the numbers, we will get this score, 0.09 instability, which means 0.91 stability. So my module should be stable, right? Who thinks it is? Who thinks it isn't? Consultants? It depends. Yeah, so it's not about the number of connections. It's about what is going on in that line. And that metric doesn't say anything about it. And in fact, here in this example, yeah, I use reflection to work with private methods of that module. And the author of that module has no idea that I'm doing that. So any change they're doing there to the implementation details, it will break the integration and cause cascading changes to my module, and as a result, to this plethora of other modules. So yeah, but hey, we have instability of 0.09. Yeah. And finally, another metric that combines them is called distance from the main sequence. The idea here is simply if your module is, the more abstract your module is, the more stable it should be. The idea is good, right? But the means of getting there, like abstractness, it's easy to cheat. If you have creative engineers, they will find creative ways to get the perfect score. But it will say nothing about the complexity of your code base. Now, to overcome these challenges, I ended up doing that stupid thing of writing that book. And who here attended my talk last year? Okay, so for you, it's going to be a little recap of some of the material. And yeah, I know last year I promised that it will be published by now, but I finished my part, okay? The manuscript is finished, it's submitted, it's going to be published soon. Anyway, today I'm going to give you a preview of some other chapters from this book. So, this book it focuses on coupling, and in fact, we can use coupling to evaluate complexity. Let's say that we have these two components. Component A references component B. That line between them, it can be synchronous, asynchronous, doesn't matter. And components, they can be classes, objects, services, whole system, doesn't matter as well. What matters is that we have that connection between them, that dependency, that integration. And once they're connected, of course, they have to exchange some data. Like one component can tell to another, hey, do something or give me some information. That data is, of course, important, but that's not the most important aspect of that integration design. Anybody wants to take a guess what's the most important part is? Not people who attended my talk last year, because you know.
Uh-oh.
Come on, somebody. Wake up, people. Sorry? Command. Close. So there is this don't repeat yourself principle. Sorry, I have to say dry and then don't repeat yourself. What is it about?
The way they're talking.
Yeah, the way they're integrating, yeah. But when we're saying don't repeat yourself, don't repeat what? Is it about code or something else? Knowledge, yes, exactly, thank you. It's about knowledge. And when two components are integrated, they have that energy of knowledge flowing between them. They have to exchange some knowledge about how each component is implemented, what it does, and how it is doing that. And we can categorize that knowledge roughly into 4 types. These 4 types in the coupling book, I call this model integration strength. So we have 4 levels: intrusive, functional, model, and contract coupling. For those of you who attended my talk last year, it was called implementation coupling. Now it's intrusive coupling, a new name. So intrusive coupling, as the name suggests, it's not something that you necessarily want in your code base. This type of connection happens when you're using something that was never intended for integration. For example, private interfaces, that example of reflection. That private method is private for a reason. But hey, I introduced intrusive coupling by using reflection and work with it. Or let's say you have a microservices-based system and, well, by now we know that we should go through the public interface to get some data from other service. But instead you go directly to its database. That's intrusive coupling, as long as that database was never intended for integration. Overall, this type of integration is, of course, fragile and implicit. Once I introduce a dependency on the implementation detail, the author of that upstream module, they have no idea that I'm doing that. So any change they're making to the implementation details has very high potential of causing cascading changes in my module as well. So knowledge-wise, we have to assume here that all knowledge about the upstream component is shared with the downstream component. So this one is all about how the upstream is implemented. Functional coupling is about what is implemented there, what functionality is implemented in those connected modules. And this type of coupling happens when both connected modules are implementing closely related business functionalities. And hey, this is the DDD conference, so I can use DDD examples. So one example would be a subdomain. Subdomain is a set of interrelated use cases. So those use cases, they have functional dependency between them. A more extreme example would be an aggregate. What do we put in an aggregate? Business logic that requires the same transactional boundaries. That's another example of functional coupling. And the most extreme example would be duplicating the same business logic or business rule in multiple modules. And if that business logic changes, both of them have to change together. That's quite implicit because they don't have to be connected physically, right? They can be absolutely different modules in the system, but you still have to change them together. So that's functional coupling. Now, functional coupling is more about the behavior. Next one, model coupling, is more about the model, the data structures that are used to model the business domain in that upstream module. Now, again, DDD conference, I don't have to tell you about the importance of making sure that your models are as good as they can be. If you suddenly have an insight how to make them better, you should. But if you have model coupling between multiple components in a system, it can be challenging because, well, now let's say you have two services that reuse the same model. You have to change both of them. And once that situation arises, then suddenly you start thinking about terms like being pragmatic, and maybe that's good enough of a model, and yeah, we can live with that, right? So that's model coupling. And again, in domain-driven design, everything within a bounded context is model coupling. We're using the same model of the business domain in the boundary of a bounded context. And finally, contract coupling. Here we have sort of a model of a model. So we have an additional integration-specific model that is intended to encapsulate as much information as possible about how that upstream is implemented. So whenever its implementation model changes, the integration contract can still remain stable. Domain-driven design, we have open host service, published language, anti-corruption layer, all these patterns. They're introducing an integration contract between bounded contexts so that if the model changes, those changes can be contained within the boundary of a bounded context. Now, going back to this diagram, so we have knowledge that's being exchanged between coupled components. However, to evaluate complexity of the design, we need something else. We also need distance. And it turns out the physical location of components in a system, it also affects the coupling. And we can observe coupling between methods, classes, objects, modules, services, systems, etc. These are what we usually call levels of abstraction. And as we go far to the right, we have higher distance between connected components. Why is that interesting? Well, because the higher the distance, the more coordination effort will be required to implement a change that affects both connected components. So we can say that the cost of change is proportional to the distance between coupled components. Again, of course, if they have to change together. Higher the distance, the more coordination and collaboration you will need to implement that cascading change. And Sonya, I think you have a good example for that.
Yeah, it's a good example of don't do that. So picture three systems: customer relationship management system, order management system, and a customer portal. Both order management system and customer portal need to know about customers, but for reasons that are completely lost to time, customer portal is getting its customer information not directly from the CRM, but through order management system. And at some point, customer portal needed more data, just one more field. So I had to go to order management people and say, could you please get that one field from the CRM so that it can just get passed down to the customer portal, because I know you don't need that data. And it took so much coordination to do that. Big distance between components, lots of coordination to make the change.
Yeah, that's an interesting example. And to understand what's going on there, let's discuss how these two measurements, how they work together. So let's say we're talking about the extremes, like low strength, low distance versus high strength, high distance. Let's say we're on this square, high distance and low strength. And here we have high distance, so yeah, implementing a change will require a coordination effort. However, that is balanced by that low integration strength. It means that we minimize the shared knowledge, and as a result, we minimize the amount of those cascading changes. So this relationship is what we usually call loose coupling. Now, the opposite, high strength over low distance. Here we have a lot of shared knowledge, a lot of changes that will affect both connected components, but because the distance between them is low, it's almost as if we are changing one component. They're close to each other. So this relationship represents what we usually call high cohesion. Again, things that have to share knowledge. There is no way around it, but they're close to each other. So that doesn't, when a change happens, it doesn't require a lot of coordination and collaboration efforts. Now, what about low strength and low distance? Is it a good one or a bad one? What do you think? A good one? A bad one? Let's see. It was a draw, by the way. So what happens here is that because of low distance, the cost of implementing a cascading change is low as well. But at the same time, we have low strength. So there won't be lots of cascading changes. But still, they're located close to each other. So now, whoever has to maintain that system, they're facing a system with lots of unrelated things located in the same boundary. Which means when that person has to change something, they have to make their way around those unrelated things and find the module that need to be changed. In other words, that person is going to face cognitive load, or in other words, complexity. So this relationship represents what's called local complexity. It increases the complexity of that component. Now, the final extreme, we have high strength over high distance. Here we have lots of cascading changes, and to make matters worse, the cost of implementing each cascading change, as is in Sonya's example, is going to be high as well. So lots of fun, and this one is complexity as well, but this one is a global complexity. So to reiterate, two types of complexities. Local is all about the complexity of the component itself. Global is the complexity of the overarching system. Now, where do we want to be on what squares do you want to be? Anybody wants to be on the local complexity or global complexity? No? Not even, it depends? Okay, cool. So we're on the same page here. By the way, I asked that question at another conference a few weeks ago, and somebody told me, if you want job security, you want that complexity. So, so yeah, there are exceptions. Anyway, so if you want to be here on loose coupling or high cohesion, that means that one of them has to be low and the second one has to be high, which means modularity can be expressed as integration strength, XOR distance. And because short equations sound smarter, let's compress it a bit. So yeah, And when I presented at another conference, someone said that it reads like me said. Yeah. Now, to apply this in practice, of course, when I'm talking about integration strength, I'm talking about essential integration strength, not accidental. If you don't need to share knowledge, remove it. But there will be cases where it's impossible to reduce it to the minimum. You will need functional coupling or model coupling. So in that case, what you have to do is to balance the distance. If you get high integration strength, then lower the distance. Low integration strength, increase the distance because these things are not related. They can be spread across multiple modules. And that brings me to a very painful slide. That one, again, finished. Should be published soon. And with that, let's wrap it up.
All right. So quick summary. From business perspective, we know that our software architecture is going to support business objectives. And what we want to measure there is its ability to change on two vectors, change frequency and change effectiveness. We can measure that with our 4 metrics that we borrowed from DORA, which is cycle time, deployment frequency, change failure rate, and mean time to recovery. Saw some pragmatic ways of measuring those, and also looked at the cost of change, which is proportional to the change complexity. And Vlad, of course, showed us what types of shared knowledge is out there and how it impacts complexity, and gave us that nice compact formula for modularity and a way of mitigating complexity with factors of integration strength and component distance. All right, and with that, thank you so much.
Thank you.